I just want to share screen. Share entire screen. It's gonna do infinity screen. So yeah, this is the chapter summary, ne? And then in this one, via Africa grade 10 study guide, we also have 41. I'll just say 43. Yeah, you need to. So this one we'll just define. So we're gonna define the properties, or rather, talk a little bit about the properties of shapes that we use in trig, and then define the trig ratios, right? So we're gonna start with at the beginning of these. And this is pretty much the summary that's given in the mind the gap, ne? So, but I just want you to get a feel of how I guess maybe in grade 12 when you started there, it's a little bit overwhelming. So they started a bit gently in grade 10 and then build it up into grade 11, etc. So 191, yeah, I'll make that 127. Your inverse functions. 191. So that's what I want to do. This is probability, analytical geometry. Still going. Still going. There we go. Trigonometry. Alright, cool. So long and short of it, trig just means measurement of triangles, right?
Okay.
Trigonometry. It means measurement of triangles, right? And yeah, so we're gonna go over the properties. So yeah, what the chapter summary is, right? So we can define trig ratios for right angled triangles, right? It's a measurement of triangles, generally speaking. So generally speaking, and that's because in grade 12 trigonometry, instead of using, like you'll see when we start trigonometry, we use it to find different measurements, right? Of either heights or distances between places. If you check on Jamboard slide 1, I'll just make an illustration. So in the primary case, we would be having, let's say a person is somewhere here, right? And
I'm refreshing.
eh?
Can you refresh and go?
Or refresh. Oh, okay. Is it slow?
Yeah, it's a bit lagging behind. Let me see, maybe it's my Wi-Fi. I've got a good one going.
Okay. Let's say you're at work, right? You said how tall do those tanks stand? Let's say this is one of the biggest tanks. 3 meters high.
Yeah, boy.
So we know this height, right? So we know this height, it's 3 meters. Alright. And let's say it's standing on the floor somewhere there. This is tank.
We're on the same Jamboard.
We should be.
Yeah, okay. They did me. Sorry.
Yeah, we should be.
I'll wait.
Has it refreshed?
Not as yet, but I'll wait. It's fine.
It says you've joined. Okay, but now even here it's slow. Infinity screen. So we know. So let's say you're standing a bit of a distance from your tanks, right? And for some reason you're curious to find out, if I know the height of this tank from the ground, can I work out how far I am from this tank if I know the angle of inclination between the floor and my line of sight to the top corner that I can see, the top edge that I can see on the tank?
Your Jamboard. Let me see.
It says you've joined us. Serious, it says you've joined. And even on my computer screen, it hasn't refreshed. I don't know if I opened the correct Jamboard, but this is the only one here, 13 May.
Yeah.
So I just closed it and opened it again. Let's try again.
But it's not here. So let me go back to the invite. Sorry.
As even on my screen, it's not showing what I've drawn on the device, on the handheld device. On the handheld device, it's drawn, but on the computer screen, it's not showing anything. And it's showing now that you've just joined.
Yeah, I closed it and opened it again.
As it, let me close and then open it again. Whiteboard.
I collab, that's the thing. So I use the link that you sent to me.
You use the link that I sent to you. I've started a new Jamboard. Oh, wait. Has it started a new? I don't know.
Okay, let's pick that one up.
Yo, duplicate as. Okay, let's start. So, trigonometry. Ne? It is measurement of triangles. There are different triangles that we have. We've got right-angled triangles. We've got isosceles triangles, where two sides are equal and two base angles are equal. We've got equilateral triangle, where all the angles are 60 and all the sides are equal. We've got acute angled triangles, where all the angles are sharp, all the interior angles are sharp, but they're not necessarily 60 degrees in size, and none of them is 90 degrees. We've got an obtuse angled triangle, where one of the angles is larger than 90. Yeah, so these ones that are not right angled, we're gonna use sine rule and cos rule, ne? And you'll see when we do those. These ones we can.
Because I can't see Jamboard.
But my Jamboard is also not. My
Left behind.
yo.
Okay, now you've just joined.
Now I've just joined.
Yeah.
It says you've just joined. On my computer screen, it's really not showing you. So let me add you again.
Can you read my test?
It shows you writing.
Yeah.
Way back it. This is so bizarre.
It's so annoying because now you've quite a few things and I can't even see one of them.
Yeah.
There we go. Okay, let's check now. Now it's writing.
Okay, but now on my screen, I'm not seeing the gestures you are presenting
I can
there.
see them on your shared screen. Check again.
Yes, on the computer screen, the shared screen, definitely they're showing. But on the tablet, which is ought to be...
Oh, because you're not in this corner of the tablet, if that even makes sense. You're
No,
not on the board.
every Jamboard I make, I just write on the tablet and it shows on the screen and you can see it. Even if I don't have it on the screen like this.
Yeah, I get you.
Yeah. I'm honestly baffled, eh?
Now you've joined.
I'm honestly baffled.
Voila.
Because now, on the tablet, I've got 2 duplicate jams. I've already written on them quite extensively. But none of them...
Delete them.
No, I'm not gonna. And I've also recorded this class.
Hey.
Yeah, so I guess the last 10 minutes have been troubleshooting. The last few minutes have been troubleshooting. Let me just close Jamboard on here. And share this screen, right? So, okay, whatever it is I'm reading from this screen that's shared now, I'll just explain and write down on the Jamboard. Okay? So, when we learn trig, we start with a right angled triangle. And we use 3 trig ratios for these right angled triangles: sine, cos, and tan. So in right angled triangles, that's where we start, and we will use sine, cos, and tan to measure the angles. And as an example, imagine you're back at the plant, right? You're standing at the floor, a bit of a distance from one of the tanks that you can visibly see without any obstruction in front of you, right? And you say that the tank's height is about 3 meters high. Maybe it has a diameter of 5 meters, let's say. So, yeah, this should look proportionate. So from where you stand, if you want to look at an object at the top edge that you can visibly see, you notice there's like an acute angle between the floor, which is horizontal, and that point there.
Yeah, sure.
So, okay, like you tilt your head to look up, is what I'm saying. So because you tilt your head, it means the line of sight of your eyes is no longer parallel to the floor.
Yeah.
Instead, it forms an angle with the floor. So now when your line of sight forms an angle with that floor, we call it an angle of inclination, right? So if you know the height of 3 meters of the tank, and you know the angle of inclination, so in other words, the angle that your line of sight makes with the horizontal plane, then you can sort of work out how far you are from the tank using trig.
Yeah.
So how you would do that is you would then construct a triangle, a right angled triangle. And if you know the distance, the vertical distance y, which is 3 meters, You don't know x, which is the distance between you and the tank. You also don't know the distance between your eyes and the top part of the tank, but you know the angle of inclination. If that angle is known, then the sine, or rather the tan of theta, yes, the tan of that angle will equal the height 3 meters divide by the distance that stands between you and the top of and the tank itself. So I just want you to bear with the explanation because Jambot Warpot, but so that I can just record this, and then I just have to make sure that you get it soon. But yo, our Jambot today, let me check the other email. Okay, I just sent you the invite again. Ish, because what I'm explaining, you need to see it. Ish.
Yeah, that's my problem.
You need to see it. Still not showing.
Saying I got my invites, came on, you shared it like 4 times already.
Let me just, you know what, let me, let me restart Jamboard.
Oh, there we go. There we go. Hello?
Yeah.
What's wrong?
Yeah, I'm still here. I'm gonna erase all of this again.
Why? Oh, to start again.
Yeah. Just erase everything.
I wonder what the problem was.
No, like, ish, the service provider I'm using, it's not very, like, the bandwidth is not very, it's not bandwidthy. So if I get like a bandwidth dip in the middle of like loading Jamboards and stuff, it does this, I suppose. So anyway, we've got different types of triangles. For now, because we're doing the basics, we'll use right-angled triangles. And we're gonna do some examples that feature this type of stuff, right? There's other triangles. We know isosceles triangles where two sides are equal and the other angles equal. I think this is the first classes we did.
Yes.
We've got equilateral triangles where all the sides are equal and all the angles are 60 degrees. We've got, this is right angled triangle. This one here, because it has a right angle. This is isosceles, this is equilateral. We've got acute angled triangle. All the angles are less than 90 degrees. We've got obtuse angled triangles where one angle is greater than 90 degrees. And I guess a host of others. But we'll just focus on this one here, because we can use trig ratios sine, cos, and tan which we define using the properties of this right-angled triangle anyway. Now, in grade 10 geometry, for right-angled triangles, we learn a very important relationship. It's called Pythagoras theorem. And it's simply that r squared, which is the hypotenuse, equals the sum of the other two sides squared. And a simple illustration of this is if you have a right-angled triangle, let's say this side is 3 units long, this one 4, 1, 2, 3, 1, 2, and this long side is 5 units long. So just to illustrate the concept of the square of the hypotenuse equals 2, 3, 4, equals the sum of the other two sides squared. So if we make the hypotenuse blue and we square the length 5 units, right? It's 5 units long. We square that side. It's going to give us an area which is 5 units times 5 units this way. So then we're going to have a lot of squares that are 1 by 1 wide and long. So we'll have 1, 2, 3, 4, and we're gonna count these squares, right, one by one after we do this. So the green side is 4 units long. Here we're gonna have 4 by 4, which is 16. And on the other side, which is shorter, that's 3 units long, right? And this is a standard triangle that you can always refer to. Like it's one of those triangles that are kind of special when it comes to knowing the sizes of the triangles. Nevertheless, we're gonna count the squares, right? So if we take this distance, which is a length, and we square it, the measurement that we get is an area. And that area is represented by this, right? Now that area equals to the sum of these two areas. So in other words, the sum of the opposite and the adjacent squared. So the adjacent squared and the opposite squared, or the x squared and the y squared, equals r squared. So we're gonna count the squares, right? In the blue area, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So here, r squared is 25. And then we're going to count the green squares. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So x squared is 16. And we're going to finish off by counting the yellow squares. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. So y squared is 9. If we take the sum of 16 and 9, how much does that give you on a calculator?
25.
It gives you 25. So this is not necessarily a proof, but I want you to visually understand that when we square a length, we get an area. Because the units for area are meters squared, and the units for length are meter. And you only get an area if you multiply a distance times a distance. That one. So because we took the distance here 5 and we squared.
Distance times
Yes, the length or a distance, when we multiply it with another distance that's not in the same direction as the first distance. At right angles. So at 90 degrees. So in other words, like think about it in terms of rectangles or squares. You have to multiply the length of one side by the length of another side that's adjacent to it. So if we're just taking one length, which is 5 meters, and we square it, then we're saying that we're taking another 5 meters, putting it at a 90-degree corner to it, and then that product becomes the area covered by that distance, 5 meters, times another distance perpendicular to it, 5 meters. So going across and the other side, like in these blue shapes here. So going this way and that way, this entire area is squared, is like the distance squared. And it's a square, so it's like one side to the power 2. If it's a rectangle, then the lengths change, so it becomes length times breadth, but we'll get to that when we do the basics of geometry and shapes, etc. But for now, I want us to focus on r squared equals x squared plus y squared. So just bear with this definition for now because it's a visual representation. Because where we're going with this, we're going to add something, which is these trigonometric ratios. These trigonometric ratios we are going to use for right angled triangles, right?
Okay, so then the square root is to get the root itself by adding the x to the y on a right angle triangle.
I'm not sure I understand.
Because it seems to me, even if the number on the hypotenuse was 10
Uh-huh.
and the other numbers were other values, the x and y would give me the root if I add them.
So, okay. I think you're trying to ask if, let's say, the triangle instead of 3, 4, and 5, it was maybe 13, 12, and 5. Let's say that's the example. Yes,
Yeah.
if you squared 13 and you squared 12 and you squared 5, if you add 12 and 12 squared and 5 squared, you should get the square of 13.
Yeah.
So when you say square root, you're implying this sign, right? Over a number. So when you say a number squared, you are representing something like this, right? Where you're gonna say
Yeah.
x squared. When you say square root of something, let's say square root
Oh
of
yes,
x
that's the
squared,
square root.
that's
Yeah.
this sign. So just be
Which is
careful
the
of
word.
the wording, yes.
Yeah.
Okay. So
So
in
it's the square root of
yes.
the root 12 squared is something else.
12 squared is 12 times 12, but the square root of 144 is 12 because it takes, yeah, it's like the reverse of squaring something. Yeah, so nevertheless, for right angled triangles, we will use sine, cos, and tan, and maybe Pythagoras depending on what we need to do. So just note that for now, ne? Why is this important? Because we have two scenarios where we can find right angled triangles. The first scenario is, let's say you're at work, finally,
Wow.
and you're standing a bit of a distance from a tank, right? We know the height of the tank is 3 meters. So if you are looking at the tank directly, your line of sight would be like this, right? Parallel to the ground. So parallel line simply means the line continue endlessly but they never touch or converge. That's parallel lines.
Yes.
Now, if you tilt your head upwards to try and look at that top corner there, it forms like an acute angle.
Yeah.
So you have an angle there. Now let's say this angle, it's obviously formed with the line parallel to the horizontal. So we can simply say then that inclination is like this. So even if it were there, because of corresponding angles, even if you shift the horizontal line below, it will still be theta nonetheless, the same measurement. So you want to measure or calculate how far you are from the tank. You can do that if you know what theta is and if you know what the height is. And you can simply use the tangent ratio where tan theta will be y over x and x would be your distance. And why is that important? Or why is this important in with regard to right angled triangles? Because this scenario here forms a right angled triangle that looks something like this,
Okay.
right? Where you have theta there, you have your y equals 3 meters, you have a right angle there, because the tank does not lean into the ground, otherwise the structure won't be stable. And the top does not make a cone unless they're shaped like that. Your tanks at work.
Yeah. Some.
Some.
Some. Yeah.
Some
Some
are.
of them are coned at the top.
Some of them are coned at the top.
Yeah. Some are coned. Some are open like this flat top.
Okay.
Yeah.
Okay, maybe there's a reason for that. But nevertheless, let's assume it's vertical for now. Let's assume it's vertical. Then that gives you don't know x, the distance, but you can calculate it if you can get a measurement of the angle that you had to tilt your head by.
Okay.
And let's say the angle for some reason is 35 degrees. Now you're gonna say tan of 35 degrees. It's all gonna be y over x, and y are 3 meters. Now if tan 35 is 3 over x, we can simply make x the subject of the formula by multiplying by x on both sides, so that x times tan of 35 degrees equals 3, and then we divide by tan of 35 degrees, so that x equals 3 over tan of 35 degrees. Now when we are using these trigonometric ratios, always it's the trig ratio and then an angle. So that angle can be a number, it can be a compound angle, it can be an unknown angle, theta, alpha, beta, x, etc. That's what theta can be. It can be a number, it can be a compound angle, it can be 90 degrees minus theta, it can be 180 degrees minus theta, but we'll get to those. For now, let's just understand that when we are doing angles, tan 35 means the angle that we're looking at is 35 degrees and we're working out the tangent of it. Now this is one scenario where I guess you can find this on your calculator, and a lot of the examples we're going to do in this class at Trig for now, the basics, are going to feature these types of problems.
Okay.
A second scenario where we find right angled triangles is on the xy plane. And we can have we can have, they call it here, it's called, okay, nevertheless, chapter summary. We can define three trigonometric ratios for right angled triangles, sine, cos, and tan. Trig helps us solve problems in 2 dimensions that involve right angled triangles, such as finding the height of a building or the distance from a building. Okay, important, ne? What we just talked about, tilting your head to look up at a height above your line of sight or the ground. That angle formed, ne, is called an angle of elevation. Because you're elevating your line of sight to see the object. If you are at the top here, the person here was at the top, and they're looking down, then that angle would be called an angle of depression. Yeah, one. So when you're looking down, let's say you're on a cliff or you're at on top of a skyscraper or rooftop of a building or whatever, and you're looking down, changing your line of sight from parallel to the ground so that it faces down to look at an object down below, then that angle formed is a angle of depression, right? That's the long and short of it. Then the second scenario where you find right angled triangles is where you have the same inclination angle and it's attached to what they call a terminal side. So this hypotenuse is called a terminal side, right? That's the name of the line that forms an angle this way between the positive x-axis and itself. And the angle formed between is still called an inclination angle or elevation angle, inclination angle, right? Now, the same inclination angle, you can also think about it as, not the inclination angle, sorry, the same terminal line that forms theta with the positive x-axis. You can think about it as a radius to a circle. You can think about it as a radius to a circle. But even within that circle, you can construct a line. So let's say that that terminal side is this blue line here. Then if you construct a line that's vertical and parallel to the y-axis, then it touches the end of that terminal side at a height that corresponds to a value on the y-axis that equals y. That is why this side is called y. And then by extension, it means where that green line is formed, that vertical line intersects the x-axis. Where that vertical line intersects the x-axis, that gives us a distance that corresponds to a certain x value, and that x value gives us a distance from the origin to I guess the point where a right angled triangle is formed. Now when we have this right angled triangle, since we said that that is a radius, we can then apply Pythagoras, but we can also apply the same sine, cos, and tan trigonometric ratios. And we can use the same principle of finding heights or distances or even angles if we know the lengths or the distances of the sides, right? And then again, on this setup, the XY axis, we've got quadrants. So now the word quadrant simply means quarter of this XY plane. And the first quarter is where X and Y are positive. So in the positive X axis and the positive Y axis. The second quadrant or quarter of this X axis, XY plane, is the one where only the X axis is negative. The third quarter part of this is where both the X axis and the Y axis are negative. And the fourth one is where only the Y axis is negative. And where the Y axis is negative and the X axis is positive. Yes. Because Y axis, yes. Where the Y axis is negative and the X axis is positive. So we're gonna refer to those as quadrants. Another important thing to note, if we're looking at a right angled triangle, regardless of scenario B or scenario A, regardless of this, let's say we have the floor there. These lines are parallel, horizontal. So if a person is standing there and they're looking at a height of a building, they form an angle of inclination or elevation, yes? But if they're standing at the top and they're looking down, they form an angle of depression. Alright, so that's the long and short of it. Now, remember when we started trig and at some point I mentioned co-functions where the sine graph starts 90 degrees later than the cos graph.
Yes.
I mentioned something like that, right?
Yeah.
Alright, cool. Yes, when you're drawing them as wave graphs. Remember that? So when we look at a right angled triangle, we're gonna look at the first way to understand that 90 degree minus thing. So when we have a right angled triangle like this, if this angle here is alpha and that angle there is beta, one of the things we've learned in geometry so far is that inside a triangle, let's call this ABC, the sum of angles equals 180 degrees. So in other words, alpha plus beta plus the 90 degree angle must equal 180 degrees. So I want to define beta in terms of alpha. So in other words, I want to have a situation where beta equals an angle, but that angle has alpha somewhere in it. And I'm going to do that so that you and I can have an understanding that inside a right-angled triangle, inside a right-angled triangle, one angle is the difference between 90 degrees and the other angle. And that's the basis of cofunctions sine and cos, sine and cos, sine and cos, differing by 90 degrees when you visualize them differently from triangles. But we're going to get to that a bit later.
90, 60, 30.
No, just the 90 degree difference.
Okay.
Yeah, just the 90 degree difference. So if I want to express beta in terms of alpha, I will have to do some maths on this equation here. Let me do some maths. So if I have beta plus alpha minus alpha plus 90 degrees minus 90 degrees equals 180 degrees minus alpha minus 90 degrees. And what I've just done, I've made additive inverses on the left hand side of the equation so that these can eliminate each other to give 0. So subtract each other out to give 0. And then I'm only left with this answer here, B, beta. And then on this side, I'll do some math and I'll reduce that to simple numbers. So this side, this gives me 0. That also gives me 0. 180 degrees minus 90 degrees is 90 degrees. And I'm left with negative alpha. And that equals beta. So this angle is 90 degrees minus alpha. Can you see that?
90 degrees minus alpha.
Yeah. And you can apply this to any right-angled triangle. You will have a triangle that's got a 90-degree angle. This will be angle X. Then this angle here is 90 degrees minus X. That's the long and short of it. You can always use that. That's a cheat sheet. All right. So yeah, I just wanted us to get that apart, that out the way. So the next set of discussions we're going to have is definitions of trigonometric ratios. So yeah, before we get into that, let's first discuss this here. So length AB is when we're talking about the angle alpha, length AB is the adjacent.
But we also express alpha in terms of beta.
Yeah, we could. And it will be 90 degrees minus beta. You can challenge yourself to prove that if you like, but you'll get the same answer. You can quickly do it. Nah. So now let's go back to our right-angled triangle. I want to draw it with our colors. So blue is hypotenuse. Blue is hypotenuse. Green is this side here, horizontal side. And yellow is vertical side, right? And we've got a 90-degree angle there. Okay, so we'll call this A, B, C. Ne? So this side is called hypotenuse. So I'll leave A, B, and B, C out for now. Ne? Because that depends on the angle that we're looking at. So let's say this is alpha and this is also beta. For now, we'll just do that now. So we're going to look at definitions. Trigonometric definitions, right? We're going to look at for alpha, and we're going to look at trigonometric definitions for beta. And we're going to define sine cos, and tan, right? For alpha and beta. So fortunately, you're not exactly new to SOHCAHTOA, so we're gonna use that. We're gonna use that just now. And I just wanna have these dividing lines, yeah. All right, cool. So I want us to color code. This part here, ne? So that we tie it visually to this diagram there. And we're gonna use SOHCAHTOA. toa. All right, cool. So, all right, the definition here, sign for alpha. Looking at this column here. The definition of sine, what is it? It's opposite over hypotenuse, yes?
Mm-hmm.
So which side is the opposite?
AB.
For angle alpha.
Is an hypotenuse. Now.
So in a right angle triangle, each side has a specific name, right?
Yeah.
The opposite side, sorry, the hypotenuse is always opposite the 90-degree angle. Ne?
Yeah.
And then the angle that we are looking at, the side that is opposite it is the opposite side. So in other words, on our triangle ABC here now on Jamboard, on triangle ABC on Jamboard, if we're talking about alpha, the side that is opposite becomes BC or CB. But the side that is opposite beta is different. It's AB. Can you see that?
Yeah.
Yeah, the side that is opposite alpha is BC, but the side that is opposite beta is AB. And now the definition of sine again, it's opposite over hypotenuse. Which side should we put as our hypotenuse? It's AC. AC, yeah. And then we're gonna go to cos. When we're looking at cos, which side is adjacent alpha? Because the adjacent side is the side that is close to the angle.
Yeah.
So it would be AB, ne?
Yeah.
And then the hypotenuse doesn't change.
Yeah.
And then for tan, it's opposite over adjacent. So our opposite is still BC. And our adjacent is AB. But now let's do for angle beta.
Mm-hmm.
For angle beta, what side is opposite?
AB.
AB, yes. And the hypotenuse is the same.
AC.
And then which side is adjacent for cos beta?
CB.
BC, okay. And the hypotenuse, I guess, remains the same. And then for tan, which side, for tan beta, which side is opposite?
It's the same as the top.
So which side is opposite angle beta?
AB.
AB. And then which side is adjacent angle beta?
BC.
BC. Alright, okay. So I want you to notice a pattern. Can you see what that pattern is in this table?
Mm-hmm.
What's the pattern? Just looking at the color coding.
Yeah, fine.
Eh?
The 10 is the same on both.
No, it's not the same.
Oh, BC. They cancel out like on the other side.
Okay, so tan alpha is not the same as tan beta, but tan beta is like an inverse of.
Yes.
Yes, it's like upside down.
An inverse, yeah.
Yeah, it's an inverse. So we're gonna discuss that inverse a little later. But then what about sine and cos? What pattern do you see there? Remember, I did the color coding intentionally.
The sign for beta is the cos for 10.
The cos for?
The sign for alpha
Uh-huh.
is the cos
Yes, that's the pattern I wanted you to see. That's the pattern I wanted you to see. Can you see something else?
Yeah, just like the sign for beta is the cos for alpha.
Cos for alpha. Alright. So I wanted you to see that pattern, right? That's that thing, yeah, in our grade 12 where we're doing the trig ratio king. Not trig ratio, we're doing reduction angles. And we're working with sine of 90 degrees minus something. Can you see okay, I'm scrolling. Yes, can you see this page here? This page here on thing. So in this right angled triangle, there are sides A, B, and C.
Yes.
And the angle opposite side B is theta. It's exactly the same as the triangle we've drawn here, right? Angle A, the angle opposite side A is 90 degrees.
Yeah.
And the angles of a triangle are supplementary. So in Australia, they add up to 180 degrees. So if we look at the sine and cosine ratios for the triangle, the sine of theta is B over A. And it's the same as the cos of 90 degrees minus theta.
Yeah.
So what does that mean? It means that that sine of alpha equals cos of 90 degrees minus alpha, because we've proven that beta is 90 degrees minus alpha. Yeah, well, and also the cos of alpha equals the sine of 90 degrees minus alpha. Because cos alpha equals sine beta. So this is the co-functions here in grade 12, how they manifest. Now, maybe later on when we get the hang of trig, we'll revise this part. But what I wanted you to bring to your attention, Gore, from 90 degrees minus theta, that's in one quadrant. When we go into the other quadrants 2, 3, and 4, we now are increasing the size of the angle that we're talking about. And we're looking at it in different quadrants. So we would need to solve for the trig ratio and the angle in that specific quadrant, because that has a governing power over the overall result of the trig ratio when we measure that angle or side of a triangle. Yeah, so if you were to think about it in terms of vectors, for example, then the thing would be, because of the cofunction, if it changes from sine 90 minus theta to negative cos theta, it would simply tell you that there has been a shift in direction, if you were to think about it in vectors, for example. That one. But I just wanted to bring to your attention how the simplest explanation for measuring right angled triangles evolves to what it becomes when we get to our metric work, which is where we're dealing with these compound angles. Now, before we finish off, I want us to do 2-3 examples from grade 10 that are similar to that tank at work example. Right? By the way, this triangle on slide 3, you can also do the same thing on a Cartesian axis. So in other words, you can challenge yourself to do the following. So the same table, we've got the hypotenuse r, we've got the vertical height y, and I guess the distance between the origin and that is x. Ne? So that's x, this is y, and this is r. So you will need to challenge yourself to define. I agree you've got access to this Jamboard. So you're gonna use SOHCAHTOA, and this is gonna be alpha and this is gonna be beta. Beta, we know it's 90 degrees minus alpha, but you don't have to write this part out for now. What you have to do is to have the sine of alpha and the sine of beta, and you define them in terms of these sides r, x, and y while referring to SOHCAHTOA. Agree, in the previous slides we used the triangle ABC, so the lengths would be represented by AB or AC or BC. So here in slide 4, you'll have to use X, Y, and R. So let's quickly do that, but I want you to be the one guessing them. Ne? So sine alpha, are you still in class? Oh no. New meeting. Sorry, it's a meeting. Yeah, what's an echo?
Yes.
Is there an echo?
Yeah.
Okay, sorry about that. So yeah, I want us to quickly go through this one. We're doing the same thing where we define the trig ratios, but we're gonna use X, Y, and R, because I get in the other triangle, it was AB, AC, and BC. So this time we're gonna use R, X, and Y, so that we see how it doesn't matter whether we're using AB, AC, or what, or X, Y, and R. As long as we know which side R is and which side X is, depending on the angle. Alright, so let's quickly do this one, this table.
Yeah.
Sine alpha would be which side over which side?
Typing.
Eh?
Yeah, you know.
So I'm asking, if we're looking at the angle alpha, which sides do we use to define sine alpha? In slide 4 of Jamboard.
Hypotenuse over.
Yes, on slide 4 of Jamboard, it's
Yes.
it's which side over hypotenuse?
It's hypotenuse over.
No, not hypotenuse. It's which side divided by hypotenuse?
It's the opposite.
Opposite, yes. Now, on our triangle that's on XY, which side is that? Is it X or Y? On slide 4 of Jamboard.
Yes, patience is with you.
Okay.
Yeah, it's Y. Sorry.
That's y, ne? Okay.
Yeah. Sorry, I was just scribbling quickly because I lost you there.
Oh, okay. So it's y over r. And then for cos alpha,
We use Y.
mm-hmm.
No. We use X over R.
Okay, that's correct.
How
And
do you
then
write that?
eh? What is that?
And use Y over
Okay.
X.
Y over x for the next one. Okay, cool. Y over x. And then let's quickly do for sine beta.
X over R.
It's going to be x over r. And then for cos beta,
And then it's Y over R.
y over r. Okay. And then for tan beta,
It's X over Y.
x over y. Okay, great. So same pattern, you see that?
X over Y, yeah.
Same pattern. The tan is like the inverse.
Yeah, for beta tan it's X over Y.
Yes. Alright, cool. So
Not X over X.
So the long and short of this is that it helps us understand one thing, ne? Depending on the angle. And that's why here I didn't write hypotenuse, opposite, or adjacent, ne? So depending on the angle, AB is adjacent alpha and opposite beta, and BC is adjacent beta but opposite alpha. Same as in this triangle. This is adjacent alpha, opposite beta, but adjacent beta is y and its opposite alpha. You see that? Yeah. So I just wanted to run that past you so that we can at least, when we jump into these examples, you get that we can use interchangeably, and we can also use that to our advantage when we're solving problems. That flexible thinking within the limits of what these rules are allows us to make the most of challenges that we come across when that we have to solve. For example, in this problem on, it's a grade 10 problem, page 392 of the Siavula text for grade 10. Ne? They say that Mandla is flying a kite, and that kite is flying at a height of 17, or rather at a distance, because we're told that the kite is on a 17-meter string. So that means that's how long the string is. And the inclination is 63 degrees. So the angle of elevation is 63 degrees. So somewhere there is his kite. Somewhere there is his kite, and that's the inclination. So we need to find the height above ground. So we'll just assume that that extends there, and the height above ground would be as so. So height above ground would be the distance y, or h, and we don't really know the distance x or distance. Let me write D or X, not, but it also spells dogs. The other one spells your. Anyway. So yeah. So we know the angle and we also know hypotenuse. Now we must find the height. If we're using trigonometric ratios, which one would you think of to use so that we can solve this problem? Let's think quick.
I'm trying to even think at all.
I know, it's been a long day. It's been a very long day. But Azish.
Okay. Would use the y over x with the tan theta of 6 and tan of 63 is wrong because the other. Yeah, it's before 90.
It's fine if we use tan. I want you to write that down. So let's say we're gonna go with tan theta equals what? Opposite over adjacent. I get y over x.
Yeah.
That's fine. Let's write that down. Write that down in your notebook.
Yeah.
So we're gonna try tan theta, ne? Now let's substitute all the information that we know.
Yeah.
So in the next step, we're gonna have tan of 63, yes?
Yes.
Okay, do we know our height?
No.
Okay, do we know the distance x?
No.
We don't. Will it be easy to solve for the height? No. So maybe not. We've just eliminated tan, so we're left with cos and sine. Which one should we try? Between sine and cos.
No. Okay. Yeah.
Take a guess, which one? Anyone? Cos.
Cos theta.
Okay, let's try cos theta. So cos theta, we're gonna write its definition. What's the definition of cos theta?
It is the adjacent over the hypotenuse.
Okay, cool, great. So now we're gonna substitute. In the next step, we're gonna write cos of the angle that we know, okay? So it's cos of 63 degrees. Yeah?
Sorry.
It's okay. So we're gonna write cos 63. Do we know x?
No.
We don't know x, ne? Do we know r? The length of the string.
Yeah, 17.
So we know 17. Okay, it's fine. So maybe we can solve for something. Yes? Probably.
Yeah.
We can solve for something, but I want us to see it through. I think we chose cos theta this time. We're still answering the first question. So we chose cos theta. We want to see if cos theta will give us the correct answer. Again? Right. So we substituted cos 63. What do we do next? We're solving for x again. What do we do next? We're going back to maths now. We're solving maths like we're in maths class. What do we do now to solve for x here? Multiplicative inverse.
I'm so confused.
No, we're not paying attention. We're trying out all the trig ratios so that we can solve for the height. Again? When solving for the height, we've already tried one trig ratio. It doesn't solve anything because we don't know two unknowns. So maybe not. We're trying the second one. We said it's cos. Again?
Yeah.
If it's going to be cos, it's fine. Now we have to solve this equation. This is a very basic equation. How do we solve it? We use multiplicative inverse, so we multiply both sides by 17 so that on the one side the 17s can divide each other out to give 1, and then on the other side we'll have 17 times cos 63. This one should not escape us, not after how long we've been spending time together. But I'll pardon just the fact our inner locos for now. And we're still learning how to use them. But nevertheless, you can punch in cos 63 in your calculator. Should give you a decimal, irrational number. You multiply it by 17. That should give you the answer for x. But does that answer our question?
No.
It doesn't. So what's the answer there?
I'm typing, sorry.
You're typing. So 17 times cos 63 is 7.718 meters. Okay. So that doesn't give us the vertical distance, but it gives us a distance that's horizontal. So that doesn't quite answer the question that's being asked, which is the height h above the ground. So we've eliminated two trig ratios. We're left with one. Which one else can we try?
Sine.
Sine, eh? So we've got sine theta. And what's the definition of sine?
Sine is the opposite by the hypotenuse.
Opposite divided by
So
hypotenuse.
it's y over 17.
So it's going to be y over r. So it's going to be h over...
R.
Oh, radius.
Oh,
Hypotenuse,
okay,
yes.
Yeah, I get it.
Yes. And then, so, yeah, we've got sine of 63. And then it equals h over 17. Now, what do we do here to solve? When we're solving, think about sine 63 as a number, right?
You sometimes say additive inverses, and then sometimes it's multiplication,
Multiplicative inverses. Because when we started our
additive inverses.
Yes. Because when we started solving algebraic expressions and equations way back in January, two of the ways that we solve for x, for example, ne? Or making something subject of the formula. Like in this case, let me just circle this here. We want to make h the subject of the formula here. Because here, we wanted to make x the subject of the formula. Right? So I mentioned those things way at the beginning, at the start, because they are the basis of us solving for equations. That one, I'm not sure. If it's still not clear, we can do another... we can always find a way to, I guess, discuss the basics of it. But solving equations is what we need to do anyway in any math problem or many of the math problems that we encounter. There's always expressing something in terms of that. There's always making this subject of formula or solving for this or simplifying. In any of those, we always have to think within how can we reduce or simplify things for ourselves. One of the best ways is multiplicative inverses. The other best way is additive inverses. And those, they help us because in these that I've circled in yellow, I would use multiplicative inverse because it eliminates the fraction on the right-hand side, for example. So that I don't have the unknown that I'm solving for as a numerator of a fraction with a number that's I've just substituted. So in order to eliminate that that fraction, I do a multiplicative inverse on both sides of the equation, where I multiply with the denominator on one side, but because I multiply with the value of the denominator on one side, on the different side of the equation, it's just multiplied by that number. So what I'm saying is this, ne? Let's look at this one here. Initially we had cos of 63 degrees equals x over 17. So I multiply both sides with the value of the denominator. Any number that I express is the same as itself divided by 1. It's the same as itself multiplied by 1. It's the same as itself to the power of 1. You get it? It's the same as itself to the power of yes. So these four things, based on the basic rules of maths, which we can always do a refresher on these. That's why when I solve problems, I always say we do additive inverse, multiplicative inverse, is to show that I don't want you to get confused. I went from this cos 63 equals x over 17 to x equals 17 times cos 63. I'm being open and transparent with the additive inverses because we've done them before, and they help because they help you follow how the problem got solved step by step. So I'll always use additive inverse, multiplicative inverse whenever I use that. I always mention it whenever I use that because it is so that you can enjoy the benefit of not missing out on what I did with each step. That's why I always use them. But they are basic tools that allow us to be able to manipulate equations to our advantage so that we can solve these same equations. Nevertheless, this same procedure, I'm applying it there, and I'm going to multiply both sides by 17. So I'm using a multiplicative inverse such that 17 times sine of 63 equals h. And the height will be 17 times 63 sine, that's 15.147 meters. Okay, so 15.147 meters is this height here. Does that answer our question? It does, because remember, sine relies on the vertical height, on the vertical distance. So because sine is using the vertical distance, it actually gets us to the answer quicker. And then the 1 year cos, we've already answered it, and that's the answer to the second part of the question. On Friday, when we do math again, we'll carry on with these types of problems so that you get a feel of how we use the calculator, how we solve the problems, and how we use trig ratios in solving these types of problems, like as we go. Is that okay?
Yeah, it's okay.
All right. But please, Nobuhlehla, I'm begging you. Additive inverse, multiplicative inverse, if those are not understood now, you're going to have a very hard time answering many maths problems. Many. Because additive inverse, multiplicative inverse, you use them in algebra, in arithmetic rather, algebra, calculus, analytical, and Euclidean geometry if you have problems that you have to solve numerically. So in literally more than 60% of your math, you will find somewhere where you have to use an additive, whether an additive inverse or multiplicative inverse. And that can be as a number or as a set of unknowns that are used as a fraction of unknowns, that type of thing. Like, if that's not clear now, it's going to be very difficult to answer some of those challenges, that those